this, depending on where you are. Okay, so that's a pleasure to welcome today Maurice Chayet from Montreal. And he's going to talk about E8, a new class of commutative non-associative algebra with a continuous Peirce spectrum.
Okay, so I can start. Well, hello, everybody. I won't say good morning or good evening or good night because I don't know exactly where you are. But basically, the idea of this talk, what I want to do in this talk is to explain the relation that exists, or the association that can be established between a simple Lie algebra and a commutative non-associative algebra, with or without unit, in fact. But in the case I'll be looking at, I'll throw in the whole thing. So you'll have an algebra with a unit, a non-associative algebra, which is very peculiar because it doesn't resemble any of the well-known associative algebras, like, for example, the Jordan Algebras, which have some special properties, namely in terms of idempotence. And this type of algebra has a very peculiar behavior because it has a continuous spectrum regarding its idempotence, as I will explain afterward. So let me start with let me say I'm going to take a point of view which is not really the point of view of the paper. It's more like the behind-the-scenes point of view, how we got to this construction, and the whole thing starts with the what is considered to be the most complicated simple Lie group, E8, and which is, in fact, to me, the simplest of the simple Lie groups, right? And you'll see why. So let me start with some comments about the exceptional groups. G2, F4, E6, and E7, and of course I'm removing E8 because for special reasons, share with the classical Lie groups the possibility of being described as a group of automorphisms of a multilinear form of small degree. By small degree, I mean degree less than 4. For example, G2 can be seen as the automorphism group of a trilinear alternating form in 7 variables. F4 as the automorphisms of a trilinear symmetric form together with a quadratic form in 26 variables. E6, the automorphisms of a trilinear symmetric form in 27 variables. And E7, the connected component of the automorphisms of a quartic in 56 variables. Of course, if you want to do that for E8, well, you immediately run into the problem that all of these descriptions I've just given you, including the descriptions of the classical Lie algebras, take place on the representation which has the smallest possible dimension. And if you try to do this for E8, well, you run into a sort of enigma. The smallest representation is the Lie algebra itself, 248. And if you want to do the same thing, well, you have to look at the polynomial of degree 8. So that's not very satisfactory. And we'll explain later on how we go around this difficulty. Now, the cases G2 and F4, and this is important for the rest of this discussion, is that they not only preserve a trilinear form, but they also preserve a bilinear symmetric invariant form, non-degenerate, and that automatically gives you the possibility of describing the group as the automorphisms of a non-associative algebra. For example, G2 would be the automorphisms of a skew vector product in C7, and therefore the automorphism group of a commutative algebra in 26 variables. So this is sort of the environment in which I want to work with for the case of E8. Just in passing, it's also known that E6 can be expressed as the connected component of the automorphisms of a 56-dimensional algebra, which is made up of 2x2 matrices with entries in a non-Dutch algebra, except that the diagonals are scalars. So let me start with an explanation of why E8 is very lies on a very singular position. The smallest representation, as I mentioned, for E8 is the adjoint representation itself. And of course, you cannot say that E8 is the automorphisms of the Lie algebra E8, but for some people, like myself, this is a bit like the dog biting its own tail. Now, Anthony Springer noticed that E8 acts as on the second smallest dimensional representation, which is of dimension 3875, with a unique invariant symmetric cubic form and a unique invariant bilinear non-degenerate form. In other words, it acts on an algebra as an automorphism group, like the previous cases, okay? Actually, Skip Garibaldi and Robert Guralnick have shown that E8 is the full automorphism group of this algebra. Now, there was a lingering question as to what this algebra is really all about. Where does it live? How this product can be described, and so on. And that was the original purpose of this search. So the first thing to say is that the representation, the second smallest representation of E8, is a sub-representation of the symmetric square. And in fact, if you look at the symmetric square, Pierre Deligne wrote an article in 1966 in which he described how the symmetric square of an exceptional Lie algebra splits. And it always splits the same way. You have the scalars, a module which is called Y2 star, and which will be the object of our talk, which corresponds here to the 3875 dimensional representation, and the Cartan component, which always appears, and which corresponds to the highest weight, twice the highest root of the Lie algebra. So this turns out to be actually the same for all the exceptional Lie algebras. Now, I would like to outline from the start, and this is the crucial thing, is that the E8 invariant algebra on Y2 star is unique because there's only one cubic form which is invariant. And so that makes it unique. However, for the other groups, G2, F4, E6, and E7, the corresponding space Y2 star has at least two distinct algebra structures which are invariant because there are at least two independent cubic forms. So you have one non-degenerate quadratic form and two cubic forms, so leading to two possible algebra structures on the corresponding Y2 star space. I've just added a small table which gives you just a reminder of the dimensions of this Y2 space for the exceptional Lie algebras. As you can see, the G2 case is 27 dimensional. That corresponds to symmetric matrices of trace 0, 7 by 7 matrices of trace 0. For F4, it's 324. For E6, it's 650. E7 is 1539. And of course, the E8 case, which we were talking about, is 3875. I've also added on the table the values of the dual Coxeter number. For those who don't know what the dual Coxeter number is, it's just essentially the inverse square norm of the highest root. Okay. Now, the first question, we want to construct this algebra. The first question to ask is how do we single out, how do we describe this Y2 module inside the symmetric square of the Lie algebra? How do we extract it? How do we describe it? There's a very nice thing which occurs. You can write up three intertwining maps from the symmetric square of the Lie algebra onto endomorphisms of the Lie algebra, a subset of endomorphisms, which are linearly independent. So this automatically allows you to take linear combinations and single out the each of the three modules which appear in the decomposition. So you have, I'm going to be using the letter K to designate the killing form on the Lie algebra. So you have a first map which maps the symmetric square onto K-symmetric endomorphisms of E8. which is given by, which I call P, and it's basically a linear combination of projection from y to x and from x to y, given by the formula there. It turns out that this map is obviously an isomorphism by dimension count. It's easy to see. There's a second map, which is also covariant, and it takes xy, the commutative product of xy, and maps that onto the product of the Jordan product of add x and add y. The Jordan product is just a times b plus b times a divided by 2. So it's the commutative association of the two operators. That is also k-symmetric because each of the adjoint maps is skew-symmetric, so the product is symmetric. And there's a third obvious map, which I call the scalar map, which takes xy and maps it onto k of xy times the identity map. All right, so there you have three intertwining maps onto the k-symmetric operators, which are linearly independent. So to answer the first question, how do we single out y2? Well, the idea is to say there's some linear combination of p, r, and I, which actually should give you something which is y2, or at best y2 plus the scalars. So I've done that. I found the proper combination. It turns out that if you look at the mapping from the symmetric square onto symmetric operators on G, which is given by the Coxeter number times R plus P, then you get something whose image avoids completely the Cartan component. So that's really the thing we wanted to do, avoid the Cartan component. So I'm going to take as definition my algebra A of G to be precisely the image of this intertwining map, as I described here, okay? So it turns out that if you look carefully, this S map, well, it obviously contains the scalars, and it also contains something else, which is the dominant weight of Y2 star, the dominant weight vector, sorry. And so A of E8 happens to be everything other than the Cartan component, L2 alpha. Okay. Another thing which we're going to work with is using representatives of Y2 star by taking S and removing the scalar part. And that's what I've done here. I have called that S plus, which you can see on the document. So S plus is basically S, to which I have removed the scalar component. Second question, what does the product look like on Y2 star? Again, I'm in the E8 case. Well, in other words, if I take two elements, S of x squared and S of y squared, S plus, because they lie in Y2 star, how do I express this product? And here's the crucial thing is that for E8, there's only one algebra structure. So that makes life very easy. Remember that if you look at the Jordan product of S plus x squared and S plus y squared, that gives you an operator on E8, which happens to be a symmetric operator. And you can take a projection onto Y2 star, or at least the image in H of G. And so any multiple of that projection actually qualifies as a suitable member for the product. After all, the product is only defined up to scalars, non-zero scalars, of course. So that gives you the first tool for getting to the product. Now, the second tool is something which is pretty nice, the Casimir operator. Actually, it's the Casimir to which I have removed the unnecessary parts. It's only the essential part of the Casimir operator. And it acts by, if you take a basis, an orthonormal basis for the Lie algebra, and so you act on an operator by multiplying on the left by add yj, and then multiplying on the right by add yj, and taking the sum. So you can see that that is E8 covariant, no problem. And so you get a nice sort of Casimir operator on H of E8 itself. And hopefully the eigenvalues of that, or the eigenspaces of that operator, should give an indication of the different pieces which make up the H of E8 decomposition. Now, another tool which I'm going to be using is based on the fact that the exceptional Lie algebras have a polynomial ring of invariants, which of degrees 2, L1, L2, etc., up to the rank. 2 is always there because of the killing form. But it turns out that the next rank is always of degree greater than or equal to 6. In fact, for E8, you have to go up to 8. Now, I'm going to use that, and this is something that was noticed by Okubo in a paper in which he published in 1979. The conclusion concerning the degrees here is that the trace of this fourth product of Rx, which is an invariant, has no choice but to be a multiple of the square of the killing form. So that is one of the formulas. And exclusively in the case of E8, you also have an extra formula which tells you that the trace of R of X6 is a multiple of the the cube of the killing form. That's only available for E8. Again, this is a miracle. Two things. First, there's only one algebra structure on Y2 star for E8. And second, you have this nice little tool, which is, as you can see, a determinant factor in defining the product formula. So the consequence of the Okubo formula for degree 4 is that you can actually compute the action of the sandwich Casimir on the images of the intertwining maps I gave you before. So omega of P, for example, is R, and omega of R is 1/6 of R plus linear combination of P and the scalar map. Having that gives you automatically access to the eigenspaces and the eigenvalues. Now, with the above description, you get 3 eigenvalues. One, which corresponds obviously to the scalars, because omega of the identity is the identity. So there the eigenvalue is 1. Then you get 2 eigenvalues, lambda plus, lambda minus. With lambda minus, I claim, corresponds to the submodule L of 2 alpha, the Cartan submodule. Now, why is that? Perhaps I'm going to explain that, because it has to do with the fact that if let's say x squared was actually should be linear combinations of this, but let's say the x squared lies in the L2 alpha module, then S of x squared is 0, right? Now, what is S? S happens to be the dual Coxeter number R of x squared plus P of x squared. Okay, so that is 0. So if you apply omega to this, you get this acting on R plus omega of P of x squared is 0. But this thing happens to be R. So you get that omega of R of x, sorry, okay, omega of R of x squared is actually minus 1 over the Coxeter number R. Okay. And you can show that either you can take either the image of P or the image of R to represent the Cartan component for H. So this shows that 1 over the 1 over the Coxeter number is actually one of the eigenvalues, and it corresponds to the L2 alpha module. Okay, And then the data above gives you the third eigenvalue, which is 1, 6 plus 1 over the Ewing-Coxton number. Okay, so having that, we know exactly how to construct the projection operator. The projection operator then has to be anything which will kill the constants and will kill the Cartan component. So that has to be a multiple of omega minus 1 and omega plus 1 over the Ewing-Coxton number. Okay, so if we apply that to the Jordan product of s plus of x squared and s plus of y squared, then we should be fine. We should get an expression for the product inside of y2 star. Now, there's just one difficulty. If you look at explicitly how you write the Jordan product between s plus x squared and s plus y squared, well, you're going to end up with fourth powers of, not really fourth powers, but the square of al x multiplied by the square of al y. So in order to be able to handle that with the Casimir, the sandwich Casimir, you have to be able to compute the value of omega on the product of out of x squared and out of y squared. Now that information is unfortunately not available from the Ockerville formula of degree 4. However, the second formula, the one that works only for E8, remember, I said there was the second miracle. That second formula allows you actually to express the value of omega on the fourth power of the adjoint map. And I've given you the expression here, you can see on the board. And this, of course, you can linearize and get exactly an expression for what you're looking for, omega of x squared and at y squared. And after some very nasty computations, I admit, which I have no intention of reproducing here, and having chosen the constants so as to make things look nice, well, you finally get the formula. And it's described here in the box. Miracle, you actually get an expression for the product inside of y2 star. Okay, so my next question, third question, would be, okay, I've got the formula on y2 star. How can I turn the A of E8 into an algebra by throwing in a unit? Okay. And of course, I want the identity map to be also the unit for this algebra. Now, there's a well-known process for pretty standard for adding a unit to an algebra, G-invariant algebra, let's say V with a binary operation star, and a non-degenerate bilinear invariant form. You can always construct the algebra by throwing in a unit with an expression of this type. There is a process of doing this with mu equals 0, but that's not very satisfactory because, first of all, it doesn't correspond to the well-known algebra constructions we know. Second, it avoids when you take the product of x and y, it just declares that the product of x and y in the big algebra is equal to 0, which is not, the x and y product in the algebra is just reduced to the ordinary product, and it doesn't have a scalar, and it doesn't reflect the fact that there's a binary relation between x and y. So for all those reasons, throwing in a multiple of the bilinear form is the thing to do. Now, let's go back to the algebra y2 star. We need, of course, if we want to do this, we need a bilinear invariant form. Okay, where do we get it? Well, it's pretty simple. You take the trace of the Jordan product of s plus xx and s plus yy. Now, in fact, for the exceptional Lie algebras, again, the Ockerville formula allows you to give you a universal expression for this bilinear form, which I've written here, which you can see there in blue. It only depends on the Ewing-Coxton number and on the killing form. Now, if you if you do this construction with the formula above, and you choose the constant suitably so as to make things look nice. After all, I can absolutely do that. There's no counterindication for not choosing the mu factor as I want. Well, you get the final expression for the algebra, which I've given here in the box. So there's the miracle. The miracle happened because one, Y2 star has a unique algebra structure. Two, there's this additional trace identity, which tells you that the trace of the sixth power of Rx is equal to a multiple of the third power of the killing form. Now, once you have that, you can start asking a lot of other questions. Just to underline some of the features of this formula. First, the identity, you can check the identity operator acts as a unit in this algebra. You can check that the normalized trace map, that's the trace of the operator divided by the dimension of the Lie algebra. In other words, so as to make the tau of the identity equal to 1, is an associative non-degenerate trace form, meaning that if you compute the trace of A times B times C, with the parentheses shown there, you will also get the trace of A times B times C, okay? And in addition, the bilinear form, the symmetric bilinear form that can be extracted from that turns out to be a non-degenerate bilinear form. There's even better, if you, I forgot to mention, but all of the arguments I've used here, I've decided to simplify everything and use the complex numbers. So everything is over the complex numbers. Now, if I make a small digression from that, it turns out that if you look at a compact real form for an exceptional Lie algebra, then this bilinear form is not only non-degenerate, but in fact it's positive definite, which is surprising, but maybe not too surprising. Finally, the algebra AOE turns out to be a simple algebra. This is an algebraic argument. All the ingredients are there. The non-degeneracy of the bilinear form is the essential ingredient. And the fact that the group acts irreducibly on components where the bilinear form is non-degenerate. That's basically the basic ingredient that makes this algebra simple. You can find that in the paper which we wrote with full arguments. You can find it in the paper we wrote with Skip. Now, the next question would be, okay, so we've got this nice formula for the product on the E8 algebra, A of E8. What's there to stop me from declaring this as a product on any other simple Lie algebra? After all, the only ingredients I need for A are, if you let me go back to the beginning, are the dual Coxeter number for the Lie algebra. So A of G is defined for any simple Lie algebra, and there's nothing preventing me from declaring this to be the actual product. Why not? Okay, so specifically, the next question you can ask is, does it work over any simple Lie algebra in general? That is, first of all, does H of G decompose into the Cartan component plus A of G? It's not obvious. It's true for the exceptional Lie algebras, but not necessarily true for all the simple Lie algebras. Is the bilinear form non-degenerate? The natural bilinear form, which consists of taking the trace of the product of X and Y, is it non-degenerate? Is it positive definite for a compact real form? And is the algebra of G simple? Well, it turns out that the answer to those questions is yes, in all cases, for all cases. Now, let me just outline how this works for the classical Lie algebras, because for the exceptional Lie algebras, aside from the fact that the algebra structure on Y2 star is not unique, once you have the product formula, you can define that to be the algebra, and everything else works because the bilinear form has the same structure and so on. First question is it true that the symmetric operators, the k-symmetric operators on G decomposes as A of G plus the Cartan component? The answer is yes. For classical Lie algebras, generally, most of them decompose as a multiple of the H of G decomposes as multiple of the identity, two irreducible submodules, and of course the Cartan component. Okay. You also have two exceptions. Well, you have the SOA case. The SOA case, well, you have three irreducible modules, J1, J2, and J3, and the Cartan component. And for the SL3 case, you have only one irreducible component besides the Cartan component and the scalars. Okay. Now, in the article, we show that all the dominant weighters of H of G modulo L2 modulo the Cartan component all lie inside of A of G. In fact, besides the Cartan component, which has dominant weight 2 alpha, we can show that the other irreducible JKs have a dominant weight vector with a non-zero image. Most of them have a dominant weight vector with non-zero image of the form S of X alpha and X beta, where alpha is the highest root and beta is a root strongly orthogonal to alpha. Okay. Now, there's two exceptions to that. The cases AN and BN. AN, for those who are not familiar with the terminology, is the n+1 by n+1 matrices of trace 0. And CN, for those who are not familiar, is the transformations on a 2n dimensional space which live in invariant symplectic form, so the symplectic groups. Okay, so in those particular cases, one of the J factors has a dominant weight vector which corresponds to the highest short root. Okay, and there the nature of the well, computations are a bit complicated. All of this is described in the article. The nature of the image in A of G can be computed, and it can be shown that it's not zero. So the conclusion is that the symmetric operators on G actually split into A of G plus the Cartan component. Okay. The other thing to notice is that the associativity of the trace form has nothing to do with the type of Lie algebra you're dealing with. It's just an algebraic consequence of the product formula. You work out the product formula for 3 terms and you get a symmetric expression. As for the non-degeneracy of the bilinear form, in the classical cases, well, one has to show basically on a case-by-case basis that it's also non-degenerate on each of the J submodules. Okay. As for the simplicity, I already mentioned that that's a consequence of non-degeneracy of the bilinear form and non-degeneracy of the bilinear form on each of the irreducible components and the action of the group and so on. Okay. Now, comments, some concluding remarks. Right? Now, these algebras A of G. Well, if you remove two cases, the SL2 case, which gives you nothing much, it gives you A of G, gives you the scalars, and A of SL3, which we saw before, had a particular structure because it was made up of basically multiples of the identity and another irreducible component. Those two cases are particular because for the SL3 case, you get, in fact, a well-known Jordan algebra, which is constructed from a trivial vector product. The product turns out to be 0. The product on the J1 component turns out to be 0. And so you get a very standard well-known Jordan algebra. So those cases are a bit special. So if you exclude that case, I don't even want to talk about the SL2 case because for me it's trivial. It shouldn't even be there. If you exclude the SL3 case, and if you take any non-zero element in the Lie algebra, you notice that S of H squared divided by K of HH, K being the killing form, is actually an idempotent of the algebra. Okay. So any non-zero element with non-zero values of K of HH gives you an idempotent. Now, if you take this to be in a Cartan subalgebra, and you look at the action of this on the dominant wave vector of type x alpha x beta, which always exists, by the way, each of these algebras is one such, and you apply the product U on S, well, you see that you get a set of eigenvalues. By varying the values of H, you get a set of eigenvalues which contains at least half of the unit interval, the full thing, right? So by duality, because if an idempotent has an eigenvalue less than a half, then there's an idempotent who has the eigenvalue opposite that, bigger than 1/2, right? So if you have idempotents that have values between 0 and 1/2, then you also have idempotents which have values between 1/2 and 1. So the conclusion is that all of these algebras, with the exception of A of SL3, have the particular property of containing the unit interval on among the pure spectrum. This is very strange, but maybe not so strange for some of you, but it's certainly very strange to me. It was a big surprise when I discovered this. Another thing that can be mentioned is that the automorphism group can be shown to lie in the connected component. There are some technical details involved here, and I'd rather let you look at them in the article. Something which we've been still working on with Skip is the fact that we've started to search for identities. Of course, natural thing to do, natural question that one can ask is, well, what happens if I have a nice commutative non-associative algebra which has some family relation to a Jordan algebra? Well, it would be natural to ask, well, can I find a defining identity of some sort? So we started looking for identities in the classical sense inside of A of G2. That is homogeneous identities among non-associative monomials of degree less than 7. We didn't find any. However, we found an identity of degree among the monomials of degree less than 7, if you take the whole set of them, which means that this identity is actually a weighted identity. Well, it turns out that we've managed to find out all the details about this identity, and we can actually write down the identity with all the coefficients, and the coefficients turn out to be G2 invariant polynomials. And there's also a strong indication that a similar identity holds for E8. Another thing I'd like to indicate is that in the exceptional cases G2, F4, E6, and E7, there's another way of representing A of G by embedding it into the endomorphisms of the smallest dimensional representation. So for F4, for example, you can map this into endomorphisms of C7 and so on. And this natural map, actually, I've given you the expression for the map in question here. It consists of assigning to S of x squared the value 6h pi of x squared. Pi is the representation, minus 1/2 of the killing form of x with itself, times the identity. And that gives you an isomorphism with embedding, gives you an embedding into endomorphism, which leads to the possibility of modeling these algebras in a computer with a much smaller I mean, less data, less with smaller matrices and so on. Well, I leave that to the specialists in modeling. I don't know too much about it. I just basically can handle a bit of math out, and that's about it. Now, the other question to which I haven't got the answer is, we know that there are at least two distinct algebra structures on Y2 star, something I mentioned before, but I have no idea how these other structures are related to the one I've just described. Okay. Well, I think I've pretty much described what these algebras are, and I'm willing to answer any questions that might be asked. Skip, do you want to add a few remarks?
Not at all, Maurice. I think you did a great job. I have nothing to add.
Thanks.
Okay, so thank you.
Thank you.
So yes, so we have time for questions and comments.
I'm just wondering. So what about D4? I mean, you missed D4.
D4.
You mentioned very briefly about SO8, but
yes,
for D4.
Yes. Well, if the D4 case, I did mention it here when I discussed about the classical cases. The D4 case is the one that has where is it here? The one that has three components: J1, J2, J3, plus the scalars. So this is a bit peculiar. The algebras of dimension 106, I believe, 105 without the unit, 106 with the unit, if I remember well. So this is a bit peculiar, and actually I had, you know, D4 happens to be part of the list given by Guralnick and considered as an exceptional group. You have, and it turns out if you try to do this embedding with D4, it doesn't work. Mm-hmm. It doesn't work because of these three components, and the other strange thing is that it looks like the automorphism group of A of D4 probably has, you know, the triality included, Z3.
Mm-hmm. Mm-hmm. Okay.
Okay, so other questions?
Have you tried to describe twisted forms of this algebra for E8?
No, actually, I'll tell you why. There's a simple reason. I don't know what a twisted form is. As strange as it may sound to you. Maybe you can tell me. No, I don't. No, really. No. I mean, I've heard about them, but honestly, I haven't looked into it.
And similarly, I mean, would it be a notion of division?
A division algebra.
You know, because for example, for Albert algebra, you have a notion of Albert division algebra.
Yes. That's a good question. I haven't spent too much time thinking about it, but I wondered about this because every time, as I mentioned before, when you take the compact real form, and you do this on the compact real form, the bilinear form is positive definite. So I was wondering whether there's, for example, I think Skip can probably tell me more about this. If you look at these algebras over fields with finite characteristics, then you can probably single out a few of them with which are division algebras. I don't know if I'm making sense, but maybe Skip can tell me.
I just say that the definition that Maurice gave in the talk works for any of the absolutely simple. If you take an absolutely simple algebraic group and you take it to the algebra, then you get one of these algebras A that Maurice was talking about. Now the question is it a division algebra when, say, the group you start with is anisotropic? I don't know. That's a good question. For small G, small groups, we can probably answer it with a computer, at least try to.
Okay, thank you. Other questions?
Yeah, I guess related to that, I guess the question is even how to define a division algebra. Because also for Jordan algebras, you don't just define it by using the multiplication, you do it like in a more complicated fashion, typically with the operators. And yeah, I don't know what the correct definition would be for division algebra.
Well, I have a tendency to like simple things. So my definition of a division algebra would be that A times B equals 1 is a possibility for all A and all B's.
Well, which is potentially too naive. I don't know.
I don't know. I like being naive. Then I discovered that things are more complicated than I thought, but I like to start by being naive. But that's a good question anyway. So I haven't really thought about it, but it's a very good question. And I suspect that this is probably over fields of finite characteristic. You can probably get a few examples of division algebras. Just a suspicion.
Okay.
Something to look into.
But before we go, we should mention that Tom, who just spoke up, also has a paper on these algebras. It takes a really different perspective, and the results are in a different direction. So the two papers are kind of complementary. And that's also on the archive.
Okay. Other question? No.
So
Okay,
if you have your, can I ask one more question?
Yes, please.
Yeah. So if you take your algebras over arbitrary fields and for completely even non-split cases, do you just use the same formula to define the algebra? Is that what's going on, or do you do it in a more complicated fashion? Or?
I'm sorry. Could you repeat the question?
Is it just a formula which is now currently on display that you use to define the algebras in all cases?
Yes, absolutely. Yes, I'm using this formula because this formula is, how can I put it? This formula is forced by E8.
Yeah, for E8, yes. Yeah.
For E8, you have no choice.
Yeah.
And there's nothing to prevent you from defining for the other ones.
Mm-hmm.
You can take that as the definition. In fact, you can check that this formula makes sense. That, in other words, that remember this formula describes how you take the product of two elements inside the image of something which is not bijective. So you still have to check that it doesn't depend on which representative of the image you have used, right? Modulo the kernel of S, the product should make sense. Now you can check that. So you can find that in the paper. And so the formula does make sense now. So it's well defined. It's well defined. It's forced to you by E8, and there you go. And it works for all the other simple Lie group, Lie algebras.
Okay. Well, thank you very much. There is one more talk next week before the holidays. Okay. So, okay. So, good weekend, everybody.
Well,
and then we'll resume in mid-September.
I'd like to thank